Hi, my name is Michael Eiler. I'm a digital lab and shop manager here at Brigham Young University in the Electrical and Computer Engineering Department. Today, in this video at least, we're going to be talking about active components, part 2. We're specifically going to be covering op amps, or operational amplifiers, and voltage regulators. Voltage regulators. Alright, so operational amplifiers, or op amps for short, are all defined or all use this basic symbol. And you'll probably see it all over the place. It's a triangle with 2 leads on one side and 1 lead on the other. Sometimes you'll see these power rails, as they're called, on the top and bottom. Let's kind of break this down. One of these is called the non-inverting input. The other is the inverting input, or the negative Vin, or negative in. We have our power plus, our power minus. This is sometimes called V plus and V minus. And then we have our V out. Okay, so that's the basic symbol of an op amp. Now obviously they're not actually triangularly shaped or shaped like triangles. Usually they come in integrated circuits, or ICs. So there'd be a chip with 4 pins sticking out. Sometimes they're 17 pins, sometimes there's 6 pins, I guess you could have, or 16. It really depends, but you'll always have to look at the datasheet to figure out what pin corresponds to what part of the op amp. All right, op amps are all defined by 3 basic rules, and if you understand these rules, you're able to extract all of the different kinds of techniques and applications for these operational amplifiers. The first of these rules is that the open loop gain is infinite, and I'm going to skip ahead to the other 3 so I don't have to keep drawing this. The next is that the positive input, or the V plus, always equals the V minus, or it tries as hard as possible to use its infinite gain, that we'll talk about in a second, rule number 1, to make V positive equal to V negative. And finally, the input impedance and the output impedance. The input impedance is negligible, so you cannot push current or draw current into or out of the input. And you can theoretically, although not practically, draw an infinite amount of current or push an infinite amount of current into or out of the output. So let's kind of draw this up one more time and we'll talk about it in more detail. I'm going to skip the power rails for now because, like I said, those are usually unnecessary. So we have our V out, we have V plus and V minus down here. Alright, so the open loop gain means that V out, if we were to use it like this, equals A times V plus minus V minus. This is the essential rule of operational amplifiers when they're in open loop. So there's no voltage or no wires connecting the input to the output. Let's clarify. This is the input, and this is obviously, by the name, the output. Okay, so if we have infinity here, we could see that, let's say we set V negative equal to ground, or 0 volts. Now all of a sudden we have V positive minus 0 volts. We can simplify that to just be infinity times V positive. So if V positive equals exactly 0 volts, or whatever V negative is, if V positive equals 0, then V out would equal 0 volts. If it's even slightly less than 0, and I guess that's much less than 0. If it was slightly less than 0, V out would equal negative infinity. And if V out was slightly greater than 0, V out would equal, you guessed it, positive infinity. The reason we can use these grand gestures or observations is because we're not mathematicians, we're engineers, so we make approximations like this. Okay, so this explains our first rule, and usually to do something like this, you would call it either a comparator, where you're comparing the input to the output, and if there's any change, you want to magnify that to the maximum voltage possible. Now, obviously, it's not going to go to negative infinity volts. It will be limited to whatever the negative power is, and same with positive, right? It's not going to go to positive infinity. It would be whatever the positive power is. That being said, that is there's a slight head room, I guess. So if you were to power this op amp with, let's say, 6 volts, you might only be able to get up to 5.4 volts if you were what's called railing, or going up to the positive power rail. Hopefully that makes sense. So in actuality, this would be a little bit less than positive power, and this would be a little bit less than negative power. or a little bit greater than, I guess, because, you know, negatives, weird things. Okay, hopefully that makes sense. But that explains our open loop gain. Another way you could use this is a Schmidt trigger. So if V positive goes over a tiny certain value, all of a sudden it's going to rail in that direction. So for this example, if instead of hooking this up to 0 volts, if we hooked it up to, let's say, 3.15 volts for some reason, now our equation would look like this. We'd have a minus 3.15 volts here. So if V positive is exactly 3.5 or 3.15 volts, then V out equals 0. If it's less than 3.5, then V out, if V positive, is less than 3.5, then V out would be equal to the negative power rail. And if it's greater than 3.5, V out would equal our positive power rail. All right. Now, they have dedicated chips for this. They're called Schmidt triggers. They're much more efficient and much more applicable. But in a pinch, you could definitely do this, and that would be understandable, depending on how bad the pinch is. I don't know. All right. Now, let's talk about our V positive and V negative. So we can use this to our advantage. Let's talk about the buffer amp really quickly. So we have a negative and positive input. If we have our input coming into the positive side or the non-inverting side, and we connect the output directly to our negative inverting side, because those two must be equal, we know that this must also be V in, which means V out equals V in. Now, you might ask, why would you ever do this, right? Why would you have essentially a component that appears to do nothing? And the reason why is it explains our last and final rule, which is input impedance is 0 or is infinite. So there's no current being able to be pushed in and no current being able to be drawn out. However, on this side, we can have as much input impedance. Oh, I'll clarify that a little bit. We can have as much current, not impedance. We can have as much current in or out of this side as we want. What this does is it uses the power rail to supply that current while maintaining the input voltage. This is known as a buffer amplifier. It essentially stops if we were to try to draw too much current on this side, it could overwhelm whatever's generating our input voltage. However, this op amp stops that from happening and only draws the current from the amp itself. Okay, I hope that makes sense. That was a little crazy, but from here we're going to go on to applications of, one more thing. We're going to talk about types. So types of op amps. You have what are called single supply and double supply. So this is something you always need to watch out for. On those power rails, our negative power and our positive power might have certain restrictions on them. Obviously, negative power should always be greater than should always be less than, not greater, yeesh. The negative power rail should always be less than the positive power rail, but that can sometimes be 0 volts. If it's 0, so for instance, let's say we're using the LM358. This op amp can be used in what's called single supply mode. So this could be anywhere from, I think the minimum is like 3 volts, maybe it's 5 volts, all the way up to, I think it's 15 volts. And this can be as low as 0 volts and go all the way down to, I think it's minus 15 volts. All right, now a double supply means that it cannot be equal to 0 volts. It has to be some threshold, usually around like minus 5 volts or something like that. That would be specific for the, let me clarify that. That's 0 volts. This would be for the LM358. This would be more expected for the LF347. Just to name one. Okay. The last thing I wanted to talk about was gain versus frequency. So typically you have what's called the slew rate. So an op amp can amplify a signal, for instance, up to a certain point. That point is the gain, right? That makes sense. You can amplify something to a certain ability. However, it's also related to and inversely proportionate to the frequency. So the higher your frequency, the lower your gain is the lower you can amplify things, essentially. And the reason why this is important is if you're trying to amplify a signal and not just a DC voltage, you have to keep that frequency in mind, because if your frequency is too fast, you might not be able to amplify it well enough or high enough to be able to be picked up by whatever instrument you're putting that signal into, whether it's a microcontroller or something else. Okay, now we're going to go into the applications of op amps. So as you can see here, I got a big list of a lot of different op amp applications that you can use. We're not going to go over all of these, but we are going to go over several of them. So the first, like I've been talking about, is boosting a signal. So these can go in two typical flavors. You have what are called inverting and non-inverting op amp configurations. So let's go over inverting first. So an inverting op amp configuration, you have a negative and a positive, and I drew that upside down. Oh, no, wait. No, I didn't draw that upside down. Ha, got it right the first time. Okay. All right, now this may look a little confusing, but I assure you it is not bad. Let's break this down into a couple pieces. So we have our input voltage, V in, right here, and we have our output voltage, V out, right over here. So we can use a couple of different rules that we talked about earlier to basically confirm or understand what this output voltage is relative to our input voltage. The first rule that we need to use is Kirchhoff's current law, is rule number 3. I think it's rule number 3 that states that there is no current into the op amp. We'll use that in conjunction with Kirchhoff's current law. So Kirchhoff's current law states that the sum of current at a node, Kirchhoff's current law. Kirchhoff's current law states that the sum of current at a node must equal 0. So if we assume we have a current flowing in right here, we'll call this I1, and we assume we have a current coming in here, we'll call that I2, and we'll guess, although poorly, that we have a current coming out. We know that the sum of these must equal 0. So 0 equals I1 plus I2 minus I3. Now we're going to apply rule number 3 of op amps, which states that there's no current flowing into or out of an op amp. So we could set that equal to 0. Now because this must equal 0, we know that I1 must equal negative I2, or in other words, I2 must be flowing that way. What the simplification does is that sets that to a negative. Oh, work with me, eraser. There we go. Which makes this a positive. Now both of these are equal to each other, and we can call it just simply I. Now that we know we have I flowing through this circuit, so I'm going to simplify this again to just be I in and I over here. Now we can use Kirchhoff's voltage law, or Ohm's law, which states that voltage equals I times R. We can calculate that the voltage drop across this resistor R sub S must give us the current, or I. Okay, so the other rule we're going to use is rule number 2, which states that the positive and negative terminals, or inputs, must be equivalent. So because of this, we can have V in minus, we'll call this V negative. That must equal the current flowing, or I, times R sub S. Now we apply rule number 2, which states that V negative equals 0, because V positive is directly connected to 0. We know simply that V in equals I times RS, or in other words, I equals V in divided by R sub S. Right, we're going to use the same rule on the other side. So we know that the current is flowing this way, so I'm going to say V negative minus V out equals I times R sub F. All right, now we know that V negative is 0 because of rule number 2. So we know that we have negative V out equals I times R sub F. Therefore, I also equals negative V out times R, or divided by R sub F. All right, we have both of these equations. They're equivalent to each other. We could set them equal to each other, and that gives us V in over Rs equals negative V out over R sub F. And finally, because we want to know the output voltage, we know that the output voltage equals Vn times negative R sub F over R sub S. This ratio is what gives us our amplification. So let's say we wanted to amplify our input voltage, say it was coming off of a microphone. So for instance, if we were trying to do audio, let's say we had a 10 millivolt signal coming off that microphone. If we wanted to amplify that to something we could measure, say 5 volts, we need this negative RF over RS to equal 5 volts, let's say. We would then, or negative 5 volts. Because if you think about it, audio signals and other signals, if it's negative, it's just shifted by 1 wavelength or half a wavelength. Okay, so RF would just have to equal 5 divided by 0.01, or in other words, 500. So we could set RS equal to 1 ohm, which is not a very good choice, but we're going to do it anyway to make the math simpler. And RF would equal 500 ohms. Now, by using this ratio, we would be able to amplify that signal or that gain by around, let me make sure I didn't do my math wrong here. I think that's right. Yep. Yeah, I'm pretty sure that's right. We would be able to get a gain of around 500, or negative 500. Okay. Now, I hope this made sense. If it didn't, you're always welcome to ask questions. In fact, I'd encourage it. So stop by the ELC and we'll talk more there. But next, we're going to go over what are called non-inverting amplifiers. Because let's say you have a signal that's not a regular frequency and you want to amplify it. Now, you wouldn't be able to use a non-inverting amplifier, or you wouldn't be able to use an inverting amplifier because you need that voltage to stay positive. Now, you could, in theory, do two inverting amplifiers feeding into each other, and that would definitely get you a non-inverted, right? Because you're negating it twice, right? But what we want to do instead is we're going to use what's called the non-inverting side, or the non-inverting style. All right, now we're going to have the positive side on top with our Vn right here, and we're going to have our negative connected to our output via a voltage divider. All right, so we have our output here, and we're going to have R1 and R2. Now, if you remember from our previous videos, and using rule number 2, we know that this is Vn. From our previous video when we talked about voltage dividers, we know that Vin, in this case, equals V out times R2 over R1 plus R2. Now this would be useful except for the fact that we want to know V out in terms of Vn and not the other way around. So we'll simply move that over to the other side and divide, and we're left with R1 plus R2 over R2 times Vn. This could be further simplified to simply be 1 plus R1 over R2 quantity times Vn. And this gives us the gain of a non-inverting amplifier. It's a little simpler to think about, which is one of the reasons why I like it. And it doesn't invert it, which is also good. And it gives you this plus 1 as a little bonus there for you. So this is a great tool. Both of these are really good tools for boosting a signal. Whether that's a small audio signal, whether that's something coming off of a some kind of measurement device like maybe a strain gauge or something else like that. You want to be able to amplify that to something you can measure. This is a perfect way to do it. Now, next we're going to be talking, and once I erase this, I should probably label exactly what those are. So this is non-inverting, or this is 1. This is 2, and you can rewind and watch the videos to get the equations. Let's see. So a buffer amp is number 3. We already talked about this one, but I'm going to put it up here again just because it's really cool, in my opinion. So I'll make it a little smaller. But essentially, let's actually derive it from this. So if we have a non-inverting signal, right, we just had this equation up, so we know V out equals Vn times 1 plus R1 over R2. Now, if we want to get this to be a buffer amp, or in other words, if we want to have a gain of 1 and only 1, what would we need to use here? Well, R2 needs to be as large as possible. So if this goes to infinity, right, by having no resistor there, just no connection to ground. And we have R1 be as small as possible by having no resistor there, meaning just a wire. We're left with a plus and a minus. And there's our buffer amp. V in, V out, and ground here, disconnected all by itself. So R2 equals infinity, or very, very large resistance. R1 is very, very small. We're going to call it 0 volts. Oops. And by using those two values, we're left with R, or V out equals V in times 1, or just V out equals V in. All right, so there's our buffer amp configuration. Nice and easy, lemon squeezy, and very, very useful. I'm going to move that up just a little bit. So we got V in, plus and a minus. Perfect, okay. And a lot of little V out there, just for kicks and giggles. Cool, okay. So you can use this for if you were to do a passive band pass filter, meaning you're using inductors or capacitors or resistors or a collection of them. You could use it to make a band pass or notch filter. Now the reason why you need a buffer filter here is if you just had a, let's see, for a band pass filter, we're letting the band go through, which means you want to have a low pass and a high pass, or sorry, a high pass followed by a low pass. There you go. So if I had a high pass followed by a low pass, so I'm going to do a terrible example and just do a quick and dirty high pass followed by a low pass. Now the problem with this is we have interference between these two circuits, right? They no longer act as they normally would because there's current flowing through here. Therefore, we need to have a buffer going between these two. So we put a buffer amp in right there. And now, theoretically, although this wouldn't be a great application of it, this could work as a band pass filter. Same thing with notch filters, although in those I think we need to use one of the other amps or other configurations, which is listed down here, a summing amplifier. But before we talk about those, let's go back to talking about voltage and current to voltage amplifier configurations. All right, so we got our buffer amp up there. Okay, so voltage to current might be useful if you wanted, say, a constant current source. Wow, look at that. So let's say we have a collection of, well, let's just say we have a motor, right? A really small motor, but it can draw different amounts of current depending on, you know, the manufacturer or things like that. So because this varies, we want to be able to control, we want to be able to have the same amount of current draw across that motor, no matter what the motor would prefer to have. We'll do that with what's called a transistor and a op amp and a constant current source. Okay, now yeah, that's kind of ugly. Let's redraw that. There we go, much better. Okay, what we have here is our Vn. We know from rule number 2 must be the same as here, Vn. And this R sense, or sense resistor, allows us to control the exact amount of current flowing from our emitter. Because remember, there's no current draw in or out of here. Because there's no current draw, all the current must come from the emitter, which must come from the collector, which must come from the amount of current flowing out of this op amp. So this op amp will regulate the voltage out here to make sure that Vn stays equal to Vn. So it will increase the voltage if need be in order to allow more current to flow here, or decrease the amount of voltage if for some reason it had too much flowing through. This configuration is called a constant current source, and it's a really powerful tool and allows you to have constant current no matter the random specifications of a given op amp, or sorry, of a given transistor or a given motor or LEDs or whatever else have you. It will always draw the same amount of current. All right, I am running out of space a little bit, so I think I'm going to erase this one just out of necessity. But you guys can always remember that in your hearts, or you can also rewind the video. Maybe I'll draw a really tiny version up here. So we got our positive and negative, that goes back around. We have our transistor. Whoa. I said small. We have our transistor here. That goes to ground, and that goes up to our load. And that goes up to power. Okay, this is number 4, our voltage current. Now let's talk about our current to voltage. So a really cool application of this is called the transimpedance amplifier configuration, and it allows us to use photodiodes, which normally will generate a current based off the amount of light hitting them, and generate that current into a measurable voltage. So we're going to put this in reverse bias, which means that anode is connected to ground instead of cathode, which is normally what you would see. We're also going to connect the positive terminal of our op-amp. Now we have a simple feedback resistor up here going to our output voltage. And what this does is the amount of light or the amount of current generated that flows this way. Oops. The amount of current that flows this way, that's better, is proportional to the amount of light that strikes the surface. But because of rule number 2, we know that this must be 0 volts. So those electrons have to come from somewhere, ergo they come from up here. This is our feedback resistor RF. So we know that the voltage out, or V out, equals RF times I, or I guess I times RF is how we normally indicate that. Therefore, the voltage out is also proportional times to RF times the amount of light striking the surface. By using really high resistors, like 500 kiloohms or something like that, we're allowed to calculate or we're capable of measuring the amount of light striking the photodiode, and use that to do some action based on the amount of light striking that surface. All right, so I'm going to erase those. And once I'm done erasing this, okay, let's see, this is number 5, our constant, or our current to voltage. All right, I could go over differencing and summing amplifiers. I don't typically use those a lot. Essentially, you would use something like a comparator, which would either sum to or subtract one from the other for differencing. So that's a pretty easy answer right there. So just your comparator, kind of like what we saw earlier. And summing, I've never had to use those. But again, if you were, like for a notch filter, I would just look it up. You're always welcome to come and ask us questions. But from now on in the video, at this point in the video, we're going to move on to voltage regulators. Voltage regulators have a variety of purposes, and we're going to go over some of those and some of the pitfalls that you need to watch out for. All right, the first that everybody always thinks of are voltage dividers. Now, voltage dividers, like we just talked about a couple seconds ago, look something like this: V in, V out, R1, and R2. Now, V out always equals R2 over R1 plus R2, but there is one crucial thing you need to keep in mind. Let me mute that before we get any distractions on here. This assumes there is no current flowing out of V out. So this is only good for signal level work, right? If you want to measure the voltage on a 12 volt battery or 9 volt battery, right? Let's say we got a 9 volt battery right here. All right, and we want to measure that with a little microcontroller that can only measure up to 5 volts. We would want to do a voltage divider to ensure that the signal coming out here is a maximum of 5 volts or less. All right, so as the voltage drops, this voltage will drop, but it will always be a ratio of those two. So you cannot use this to power anything. If you do, two bad things will happen. First, the equation will break, which means your math is wrong. The second, and probably more important, is you are dumping immense amounts of power over these resistors, which will, in essence, turn into heaters and catch on fire. So please, voltage dividers are great, but only for dividing signal level voltage or regulating a voltage at the signal level. Next, let's talk about linear voltage regulators. Now, these are often described as a L... no, I don't actually think there's an L. There might be. It might be a L7XXX. Okay. Now, if I saw a package like this, and I guess technically that's also an option, that could be a 5, but you almost always see it as a 7. So an LM, for instance, 7805. Let's talk about that. So the 78, the 8 part right here tells me it's a positive, otherwise it'd be a 9. 9s are negative. Oops. Negative voltage. And the 05 tells me that it's 5 volts. Pretty simple. So if we instead saw a LM, let's say a 7912, that would tell us it's a negative 12 volt regulator. Or if we saw a 7806, that would tell us that it's a 6 volt regulator, positive 6 volt regulator. Okay. There are also other packages like the LM1117, which is a variable one, and so on and so forth. These are what are called linear voltage regulators. They're good for a medium amount of current. The ones we sell here at the shop are good up to 1.5 amps. However, one thing you need to be aware of is all of that extra power. So let's say we're using this to convert 9 volts down to 5 volts. So let's use the LM7805. All right, those typically have a ground connection for 1 pin. They have a capacitor in front, typically a 0.33 microfarad, and another smoothing capacitor in the back, usually a 0.1 microfarad or 0.01. All right, and that goes to ground. Okay, and then we get 5 volts out. So if we just look at the math here, if we're drawing, let's say 1 amp, right, the power being dissipated by this voltage regulator is equal to the current times the voltage being dropped. So in this case, it'd be 1 amp times 4 volts of power, or 4 volts, which means that we're burning off, in essence, 4 watts of power by this chip. Now, they're capable of doing this. They can do it, but it's really, really hard on the system. So typically, I only like to use linear voltage regulators if it's an application that makes sense, so I don't have room for something more efficient, or if it is just small, it needs to be compact, or if I don't really care about my power usage. Now, if I was doing something with a battery that had to last for a long time, I would look at other applications or other possibilities. But yeah, in long story short, you don't like to waste 4 watts of power whenever this thing is turned on, or whenever we're drawing 5 volts off of this. It's just not necessary, and it's not essential. So I like to use it for medium amounts of current, preferably less. And efficiency, in terms of efficiency, we're only getting, of the 9 watts that we're using, we're burning off 4, so we only get 5 watts. So 5 watts divided by 9 watts, that's a little over 50% efficiency. That's pretty awful. Let's talk about switching mode power supplies. They come in 2 different varieties, bucks and boosts, or sometimes you can find buck boosts. But these are for much higher currents. 3 amps is very typical. And they're high efficiency. We're talking like 80 to 90% efficiency with these things, even at those high currents. They're very, very great and very, very useful. So a buck is easily recognized because it bucks off the extra voltage, and a boost will boost the voltage to something more useful. So how these work in essence, I'm not going to go into a lot of detail here, is essentially for these, they're called switching modes because they're switching on and off. So you have your VIN that goes on, typically it's you got a chip, you probably have an inductive coil, and then you have a smoothing capacitor or 2 or 3. They use the kind of the natural cycle, the frequency of this circuit to turn itself on and off. They also have a transistor to drive this whole thing, to turn itself on and off fast enough that, as far as we're concerned, V out is exactly what we need it to be, and we're not wasting anything because it's turning itself on and off really quick, and then we got this kind of smoothing capacitor to smooth out that voltage output. So we're never really we're never really losing that much power, right? We're essentially turning it off so fast that the power drain is smoothed out by the capacitor, and we get this nice smooth output voltage that's much lower than the voltage we're putting in. So you can see ones where you can put up to like 48 volts in and get 5 volts out and still maintain this high efficiency. They're very, very excellent. The switching speed is also high enough usually that you don't have to worry about interference in your circuit. But if you did, you could always feed it through a linear voltage regulator after that with more smoothing capacitors to kind of clear anything out. So that's the long story short. I'm not super familiar with how these work usually because I just get them off the shelf. But if you wanted to build one, you could always kind of look at one, figure out what chips they're using, and then go from there and select necessary components. Basically, use the data sheets. That's why they're there, and that's why they're important. I do have one extra treat for you guys. We're going to talk briefly about microcontrollers today. Really, all we wanted to focus on is kind of what to look for when you're selecting them. Right off the bat, you want to be aware of how many pins do I need, right? Do I need a lot of digital pins, measuring, button pushes or simple switches, things like that? Do I need a lot of analog pins? Maybe I'm measuring ambient light or temperature or other analog signals. Do I need a lot of PWM? If I'm driving servos, for instance, the Arduino package, which is great and one that we use all the time, is kind of limited in that sense. It only has 6 PWM channels, whereas the ESP32, don't get me wrong, 6 isn't bad. The AT-Tiny 85 only has 2, right? So 6 is better than that. The ESP32, though, has 16 PWM channels. So if you need PWM, the ESP32 is definitely the way to go. But for instance, going beyond that, clock speed. For everything most hobbyist electronics or personal projects or a lot of undergrad stuff even, clock speed is not a huge issue, right? We're already talking in the megahertz, and you're pretty fine doing whatever you need to at that speed. But if you are doing something higher frequency, by all means, look at the clock speed. See if it's something that can go high enough for what you require. Memory is another big killer for a lot of projects. For instance, we sell these little OLED screens. They're great. They're nice little compact things that have 4 pins. It's I2C communication. However, the default library to use these is large enough that you need the 328p processor by the Arduino package, for instance, for the Atmega 328p. If you don't have that big processor, if you're using the 168, it's not going to fit. It just can't support the entire library that you need to use that OLED screen. Communication protocols are another one. So I just mentioned one, I2C. So we got I2C, we have SPI, which stands for Serial Peripheral Interface. You have Serial, that's another good one. You have UART. Whoops. You have Bluetooth, right? The ESP32 can do Bluetooth, which is great. We also sell the HC05, which is a Bluetooth chip, basically an antenna. Let's do BT for Bluetooth. There's also Wi-Fi, right? That's another good protocol. A lot of these will still use serial kind of underneath, but it's great to know what your project really needs and then kind of pick the chip based off of that and not go the other way around, right? You never want to pick a microcontroller and then force your project to fit it when you could just pick a better microcontroller to start with. The next is operating voltage. This one is really important because sometimes you don't want to have a big honking battery on your board if you don't need that. That's one of the reasons why we like the AT-Tiny 85 is, as opposed to the Arduino, which needs a minimum of 5 volts typically. 5 volts up to, I think you could power it up to like 17 volts, although it's not great, right? You're using a linear voltage regulator, so 12 is better. The AT-Tiny can go as low as, I think it's 1.18. I might be wrong there. And a max of 5.5. Now, this one, obviously, right, you have a lot more pins, a lot more you can do with it. But the AT-Tiny package, especially the AT-Tiny 85 that we sell, if all you're using is like 2 or 3 pins and maybe only 1 PWM channel, right, you can totally use this package and you only need a coin cell, right, which spits out a nice 3.3 volts. Or if you use one, AA battery or one AAA battery, those are 1.5 volts. That's inside. That might actually be 1.8. And if it is, then this wouldn't work. But if you use 2 of those and you get 3 volts, all of a sudden you're back in business. Around a 1 volt. We'll just put it that way. All of a sudden you can use these smaller batteries and you don't need to worry about a buck converter or a boost converter to bump it up or bump it down. You're able to have much higher efficiencies, and that's just better across the board for longevity and project duration, in essence. The next one is interrupts. Now this is one that you use if you don't want to write blocking code, which is really important. But let's say you wanted to have a deep sleep mode, or let's say you wanted to have it so if somebody hits a reset button, no matter what's going on, it's going to reset itself, right? Those all use interrupts. So make sure that if you do need something that can operate asynchronous, that you have sufficient interrupts, whether that's pin interrupts or timer interrupts or both. That's important. And then finally, sleep mode. That's kind of part of that. That allows us to do very, very long projects with a small thing. I recently worked on a project that used an AT-Tiny 85, and with a single coin cell, right? It's a 3.3 volt battery with 200 milliamp hour, I think. I was able to get that theoretically to run for 5 months by just putting it to sleep until one of the pin states changed, and it would wake up and run its routine and then go back to sleep. So having sleep mode is very, very great. Usually for the Atmega, that's indicated by a P, so the 328 versus the 328P. That's kind of that difference there is that power, extra power performance. So that's what to look for. Anyway, that sums up our video today. Was a little harebrained. Sorry, I'm getting over a cold. If you have any questions, if anything was unclear, please, by all means, email us, come by the shop, come by the ELC, and we'd love to help. And yeah, we'll see you in the next video. Thanks so much.